Hello, everyone. Welcome back. Today, we're going to be talking about these big four reactions. We're going to go through and we're going to identify how you should approach these in terms of a problem-solving sense. Because on the exam, what's going to be put in front of you is going to be a set of questions that essentially just say predict the product, right? So you're looking at what is the major product that is formed from a reaction, right? And for these types of problems, it'll look something like this. You'll have some reagents, you'll have your reaction arrow, and then there's going to be a box that pretty much just says, all right, what goes over here? And so essentially, what we're going to be doing in all of today's lecture is we're just going to be talking about the how do you approach this, right? Because I want to make sure that everyone is comfortable with approaching these types of problems. And the first thing that I have to say about approaching these types of problems is whenever you want to do so, you need to make sure that you are comfortable with all of the types of reactions we've talked about thus far. So if you're not comfortable with those reactions, please go back and watch some of those lecture videos, do some practice problems. But then whenever you feel that you're comfortable with each type of reaction, what they can do, you can move on to doing this. So, if we're given something like this problem here, the first thing that you want to do in order to figure out what the product is you want to identify the type of reaction that we're looking at, right? So that is going to be our first step. So when we're identifying the reaction type, right, the first thing we want to do is we want to figure out what is going on with the leaving group. And the first thing to do to figure out what's going on with the leaving group is we need to find the leaving group, right? Because if there is a leaving group, these reactions can occur. But remember that for all of these reactions, it needs a good leaving group. So if there isn't a good leaving group, then none of these reactions are actually going to be the operant mechanism that's occurring. And then once you've found it, you're going to want to identify the type of carbon the leaving group is on. Okay? And the reason this matters is because if we're bringing together everything that we've talked about from these other lectures, essentially, we have three different types of carbons that we're really paying attention to. That's primary, secondary, and tertiaries, right? Because those are the types of leaving groups that we see most commonly. And we talked about how on primary carbons, you cannot do SN1 or E1, right? That leaves us with the options of on a primary carbon, you can either do SN2 or E2, right? If the leaving group is on a secondary carbon, technically everything is possible, right? So SN1, SN2, E1, and E2 are all possible if the leaving group is secondary. The third thing for those tertiaries is remember that tertiary carbons you cannot perform SN2. So that at least brings us down to it can be SN1, E1, or E2. Now, with all of that being said, the main purpose of figuring out what type of carbon the leaving group is on is that if it's a primary or a tertiary, it eliminates some possibilities. Now, with that being said, it doesn't eliminate all of them, right? Especially not on a secondary where everything can occur. So the second thing that you're going to want to do is once you've figured out what type of carbon the leaving group is on, you're going to want to then identify if your nucleophile is strong or weak. Because as a reminder, that can actually change what type of reaction we are looking at. We talked about for SN2 and E2, they require strong nucleophiles, right? So if it's strong, you can immediately narrow down it is SN2 or E2, right? And then if it's weak, on the other hand, we talked about how it's not possible to do SN2 or E2, so this must be SN1 or E1. And as a reminder, one thing that's really nice is if you identify something as a weak nucleophile, remember SN1 and E1 both occur together. So in reality, you don't have to go ahead and try to weigh which one of those is going to be more prominent because both of them are going to happen at the same time. On the other hand, with those strong nucleophiles, SN2 or E2, sometimes this eliminates all your possibilities and narrows it down to one. But there's one issue, and that is, say it's like a secondary or a primary leaving group that we have going on, right? Both of those can do SN2 or E2. So the third thing that we want to do is this is if it is a strong nucleophile, right? This is if you can't figure out SN2 or E2. Right? You're going to do two different things, right? The first, which we'll just say is A, is you're going to check other sterics, right? So it's not just the carbon that the leaving group is on, but the surrounding carbons can also force you to go into an E2 type of mechanism. The second thing that we care about is check the conjugate acid pKa. And so what this ends up doing for us is that we now have a couple of split categories. If the conjugate acid pKa of your nucleophile is less than 25 and we're on something like a primary or secondary, 99% of the time this is going to be an SN2. Versus if your conjugate acid pKa is above 25, right? This is generally showing that it's probably an E2. Okay, so that pKa dividing line is useful to determining one versus the other. The other thing that we need to keep in mind is if it is a sterically hindered base or carbon surrounding the leaving group, it's probably also going to force us to do E2. Okay, and the other thing to say about this is that also E2 happens much slower on primary carbons, right? And that's just because it forms less stable alkenes. So there's a lot more checks that we have to go through if it's SN2 or E2, right? But we'll get to those whenever we do some of these practice problems here. The last little thing that we want to pay attention to, and this is if some of these rules have been broken. For example, if no leaving group is present, don't just assume no reaction can occur, right? I would say look for evidence of acid-base chemistry or other reactions. Okay? So some things to keep in mind. For this lecture, we're going to go through multiple examples that are going to allow us to use these ideas and problem solve our way through some example problems. So let's go back to that first one, right? We will call this example one. So for this one, we saw it was a alkyl bromide. We had sodium cyanide, THF at 70 degrees Celsius. So the question becomes, what type of reaction is this? Right? First thing we want to do is we want to figure out what type of carbon our leaving group is on. Looking over here, it is on a primary carbon. What this immediately tells us is that it's not possible for us to do SN1 or E1, right? The other thing is if we take a look up here, sodium cyanide, right, it breaks up into what is the Cn minus and then sodium with a positive charge. And anytime you see that negative charge right there, you got to think that it is strong, right? All of this leads us to believe that it is not possible for SN1 or E1 to occur, right? So this is just not a possibility in this reaction. Now then, looking at these other pieces, now we have to determine, is it SN2 or is it E2? Well, looking at our nucleophile slash base, it is Cn minus. Now, if this was our base, then the conjugate acid would be HCN. HCN has a pKa equal to 10. So odds are this is going to do SN2. This is even better supported by the fact that this primary carbon will be faster for an SN2 reaction to occur. So in that case, I can say confidently that this will be an SN2 reaction, right? That will be the fastest possible reaction we can do. And so with that, what that means for us is if this is an SN2, and the reason that I said at the start of this lecture, you need to understand what each of these reactions does, is that once you know what reaction it is, you have to then be able to show the product of that type of reaction. So what's the product of an SN2 here? Well, it would be our cyanide anion doing a backside attack, kicking out the bromine, and substituting it. Right, so now we would have a CN where the bromine once was. So if we were drawing out the product of this reaction, it would be the cyanide right there. So that would be an example of how we approach these types of problems. All right, let's go ahead and let's do another one. This will be example two. So let's say for this one, we're doing this here. All right, so step one, we need to figure out what is going on here. So we see our leaving group is this OMS, right? Because remember that is one of those sulfuric acid derivatives. And so it is currently sitting on a tertiary carbon. What that tertiary carbon tells us is essentially there will be no SN2 here. All right? So we can mark that one off the list of reactions that can occur. Now then, if we want to take a look over at our nucleophile slash base, we see that it is NH2 minus sodium cation, right? That negative charge tells us that it is strong, which means no SN1 or E1. So this has actually very easily narrowed us down to where we can say this is an E2 reaction, right? Because if it's on a tertiary, we can't do SN2. If it's strong, we can't do SN1 or E1. So it must be E2. The thing with E2 reactions is they then lead us to another couple sets of questions, right? These are usually the hardest ones to actually make the product for, because now that we've figured out that it's an E2 reaction, we have two things to worry about. First is remember we have to be looking for anti-paraplanar hydrogens. And then second, we have to worry about if it is the Zaitsev or Hofmann product. So, looking at this exact reaction, let's start by talking about is it Zaitsev or Hofmann? Well, the base is NH2 minus, right? Which means that this thing is relatively small. And as a reminder, small bases are much better at forming the Zaitsev product or the most substituted, right? So this will form the most substituted alkene as it is Zaitsev. Now then, we have to look for some anti-paraplanar hydrogens. Well, to do that, let's redraw our starting material and let's label the alpha positions, right? Because as a reminder, we have to have an alpha proton in order to do an E2 reaction. So we actually have three alpha positions here, right? Because this is tertiary. So we have the alpha position to the right, the alpha position to the left, and then we have that methyl group that is also alpha. So looking at this, it immediately makes sense to say, okay, well, the most substituted alkene would have to be either to the left or the right, and since this molecule is symmetric, either one is fine. But because this would be trisubstituted if it were an alkene. So that's fantastic, right? But there is one minor problem. If we look at where the hydrogens are on this structure, right, remember that this OMS has to be either wedged or dashed. It's a racemic mixture, so it doesn't matter in this case. So let's just put it on one to begin with, right? Let's shove it on that there. If we were to draw on this hydrogen, where does it sit? Well, it's actually on an sp2 carbon, right? That is sp2 hybridized. So the hydrogen is in plane. Now, the reason this is a problem is because if we want it to be anti-paraplanar, it has to be 180 degrees from the leaving group. That's not possible if it is in the plane, right? Instead, what it'll be is it'll just be facing in a direction that we could never rotate this mesyl group into. So essentially what this is saying is since it's planar, the hydrogen can't be anti to the OMS. Because remember that if we wanted one to be anti, it would have to be on a wedge. And you can't have something on a wedge if it is completely flat. So essentially what this means is it's all because that mesyl group is on an sp3 tetrahedral carbon. So what we're looking at is we actually have an interesting statement about E2 that we can make here. And that is for E2, if the leaving group is on an sp3 hybridized carbon, then the hydrogen must also be on an sp3 hybridized carbon. Now, that being said, we're going to find out in just a little bit in another example that if the leaving group is on an sp2 hybridized carbon, the H must also be on an sp2 hybridized carbon. Okay? So we'll use this in a little bit, but this is a useful rule of E2 to keep in mind. And it all has to do with that anti-paraplanar hydrogen. So, are there any anti-paraplanar hydrogens? Well, yes, because notice that this alpha position up here that we had ignored earlier is in fact sp3 hybridized. And it has some protons up there. So, because of that, we would see that in the mechanism, right, if we were to even draw this in as a wedge and then the mesyl group on the dash, there's always a hydrogen here of these three that exists that will be 180 degrees from the mesyl group. So then our NH2 minus can come in, it can grab one of those protons, form the alkene, kick out the mesyl group, and we now have the di-substituted alkene right there. So in reality, for this predicted product, the final product is that right there. So this is the other reason that I said before, knowing the reactions is incredibly important because being able to identify what the reaction is very good, but then you really need to understand the reaction in order to get the correct product. All right, let's go on to another example. Right, we'll be going through quite a few other examples during this. But for this one, let's take a look at something that is also an sp2 hybridized carbon. So let's say we were working with this alkyl iodide, and we're doing H2O 100 degrees Celsius. Well, looking at this and thinking about it, the first thing that you would want to do is you'd want to identify what type of carbon the iodide is on. And so remember that when we talked about primary, secondary, tertiary, we couldn't include some types of carbons. And those types of carbons were the ones that were different hybridizations. So rather than this, which looks like a secondary carbon, being called secondary, instead we called it sp2. And so sp2 did not fit into any of our rules. So what do we do? Well, if we think about what this reaction should be, right, looking at the nucleophile that we have present, this is weak. So we would say that this is likely SN1/E1, right? But let's think about what this mechanism would look like. Well, this mechanism would start out the same way that all SN1 and E1 mechanisms start out. The iodide would leave as the leaving group, right? From here, we would generate a carbocation. But this guy is surprisingly very, very unstable, right? Even more unstable than a primary carbocation. And as we know, you can't do SN1 or E1 on a primary carbocation. So why is this less stable than a primary carbocation? Well, if you take a look at what this looks like in terms of the actual orbital drawing, right? If this was our structure, we have some p orbitals that are hanging out, making up the alkene in this scenario, right? So essentially, these are just the alkene bond being shown as a pi bond. Now then, where does our positive charge sit? Well, the positive charge in this case would not be able to sit in a p orbital facing that direction, right? Because essentially what we're saying is that spot where that p orbital is already occupied. So instead the positive charge is sticking out like to the side right here. Notice that in this orientation, it is not flat, right? It is still or well, hard to say that it's not flat. It's just not facing in a direction that can be overlapped by other hyperconjugation. Because remember, if we think about hyperconjugation, it would be this carbon with this hydrogen right here that's donating towards something. What is it donating towards? Well, it's actually donating towards our alkene, right? So essentially what we're saying is that in this case, the positive charge has no hyperconjugation or resonance to stabilize. And the reason that's worse than something like a primary carbocation is at least the primary has one CH bond that can do the hyperconjugation. So this is even obvious if you look at BDEs, right? Because these define our radical stability. Looking at BDEs, if we were to have something like this primary carbon right here, you would see that this has a BDE of 98 kilocalories per mole versus if you have the same thing, but now it's an sp2 hybridized carbon, right? This BDE would be 111 kilocalories per mole, right? So this is much higher energy, which means it is a stronger bond, which also means that it is going to form a less stable radical. Okay? So that's another reason that this reaction is not going to go well. It has a very strong bond between that iodine and that carbon. And so since this is so high energy, this cannot occur. And if this can't occur, essentially what we're saying is that this right here must be no reaction. All right? So essentially, one thing to keep in mind about SN1 and E1 is that SN1 and E1 can't occur on sp2 carbon leaving groups. Okay? What about if we changed this up a little bit and we tried to use those conditions from one of the first examples to do something like SN2, right? So if we wanted to do SN2, let's use the exact same conditions from the first example where we had sodium cyanide, THF, right? We know that this is going to be an SN2 reaction. But thinking about it, let's say we tried to do the same thing this time where we took that Cn minus and did a backside attack and added in here. Well, in this case, doing the backside attack isn't super hard, right? There's relatively minimal sterics. I mean, there's hydrogen sticking out here that'll get you into a little bit of trouble, right? So it's more sterics than a general secondary, but it's not impossible. The main thing is just this bond is still way too strong. So essentially, what this means is that The slightly increased sterics increases the activation energy enough to where this super strong bond you can't do SN2 on. All right. So essentially for this, it's still no reaction, right? Because SN2 also can't occur on sp2 hybridized carbon leaving groups, right? But then brings up the last question, what about E2? Well, E2 is different, right? Because E2 kind of breaks a couple of rules due to how strong bases are, right? If we were to use the same conditions that we used for the second example for E2, so being NaNH2 THF, right, under some heat, what we'd find is that this will actually do E2. And the reason for this is E2 is going to form such a strong bond between the base and the hydrogen. And in this case, the hydrogens, we have two of them on the alkene, right? Since these are in plane, this one right here is actually antiparaplanar to the iodide, right? So this is what we talked about earlier in that other example. If we have an sp2 hybridized leaving group and we have sp2 hybridized CH bonds, right? These can actually be anti. And so what this ends up doing is if your base is strong enough, which it has to be a very strong base, keep in mind. So we're talking about pKa of the conjugate acid being like 35 plus, such as this here. What it'll do is the base has enough energy that it can form that, in this case, nitrogen hydrogen bond, make another pi bond there, kick out the leaving group. And if we're already making a pi bond on something that has a pi bond, it is actually going to make a triple bond. So this type of reaction for E2 forms triple bonds, right? All in all, though, I will not test you on this for the exam, okay? So keep in mind, this won't be tested on your exam. But I will make sure that you're aware that the other reactions can't occur with sp2 hybridized leaving groups. Okay? So essentially, if we think about it, for sp2 hybridized carbons with leaving groups, essentially E2 can happen sometimes, but none of the others can. Okay? So let's go on to another example that's back to the relative normal examples that we've been looking at. So for this one, let's say that we had a structure that looks like this. Okay. So for this structure here, first we got to figure out what type of carbon the leaving group is on. In this case, it's a secondary. So every reaction is technically possible. But then looking at this here, there is no charge. That tells us that this is weak. All right. Anytime we see something that's weak, it's immediately true. That thing is going to be SN1 or E1 if possible. In this case, with the secondary carbon, it is possible. So, how's this going to work? Well, let's draw out a mechanism, right? Because again, you can get to the point that you can do these immediately when looking at them. But just to help people out and make sure that they understand the reactions, we're going to go through the mechanism anyway. So, for this mechanism, right, if it's SN1 or E1, the first thing that happens in both of these is that our leaving group leaves. Right? Upon leaving, we are left with a carbocation. At this point, remember, one thing that you always have to do with these is you need to check for rearrangements. All right? Because our SN1 and E1 reactions can do rearrangements. In this case, we're on a secondary carbocation, right? And surrounding us is just other secondaries. So nothing's going to happen in terms of rearrangements. In that case, what we can do is we'll use this top line as the SN1 path, and then the bottom one is our E1 pathway, right? So looking at this, we'll just draw the same structure because this is where they split off. For SN1, what we see is that our thiol, which is acting as our nucleophile, it's going to come in and it's going to attack that carbon that the carbocation's on. And so we're going to form that carbon-sulfur bond. That's going to leave our sulfur with that methyl group and the hydrogen still attached. So now it has three bonds as a positive charge. So from here, another equivalent of the thiol is going to come around, grab that proton, give the electrons back to the sulfur to now make it a neutral thioether. All right. And so this is our SN1 product. Now then, on the E1 pathway, what we see is this one's a little quicker. We have two alpha positions, right? They would be right here and right here. They're both the same because this is symmetric. So either one we can take a hydrogen from. In this case, I'll take one from the right. So our thiol is going to act as our base that comes in, grabs that proton, and then it's going to form the alkene between the carbocation carbon and the carbon that that proton is on. And so this generates our E1 product. So on the exam, if you're asked for this question, what you would provide as the major products would be the thioether that comes from SN1 and the alkene that comes from E1. Let's do another. So this will be example 5. So on this example, we are going to see this as our reactant. Then we're going to have some KOTBU, HOTBU at 80 degrees Celsius. So for this one, if we look at what carbon our leaving group is on, it's on a secondary, right? That tells us it can be any reaction. But then looking at our nucleophile here, positively charged potassium, which means we have this tert butoxide anion. This is strong, right? So looking at this, it could be SN2 or E2. But the thing here is if we look at what that TBU actually means down here, we would see that it is tert butyl, right? And we know that SN2 is worse whenever it comes to bulky things. And looking at this, it has high steric bulk. So this is that scenario where looking at the steric bulk of the base or nucleophile can tell you that this is in fact going to be an E2 reaction. So we know that it's E2, which means now we need to do the things that we did last time, where we need to first determine is it Zaitsev or Hofmann, right? So knowing that this has high steric bulk, that immediately leads us to believe that it is going to be Hofmann, right? And as a reminder, Hofmann is going to form the least stable or least substituted alkene. Okay, so what is that going to look like on here? Well, let's go back and redraw our original molecule. And let's think about our alpha positions. Since we're on a secondary, there's going to be two alpha positions. We have this one here. We have that one there. We can imagine if we form an alkene on the right-hand side of where the bromine is, this would end up being a tri-substituted alkene. Versus if we form one on the left-hand side, it would be di-substituted. So what this tells us is since we want a Hofmann product, the di-substituted one is going to be the favored one in this case. Okay? So we're going to be using this alpha position to actually do our chemistry. So if we want to look at the mechanism of this reaction, right, we have our bromine here. It's on a dash. Our hydrogen needs to be anti to it. There is one hydrogen on a wedge and one hydrogen on a dash right here. And we know that the one on the wedge is going to be 180 degrees from the dashed bromine. So what that means is that for this E2 mechanism, it's going to grab that proton, form the alkene, kick out the bromide, and we're going to end up with this E alkene as our product. All right, so if we were to draw that up here, the answer to this predict the product would be that structure. Let's do another one. Okay, so for this one, we will start out with this structure here as our reactant, and then we will use this here. This time we'll do DCM at 20 degrees. So for this reaction, as normal, first thing we have to do, figure out exactly what is going on here. It's on a secondary carbon, which means it can be anything. But then looking at our nucleophile, right, we see that it is a negatively charged sulfur with that sodium anion. So that tells us that this here is indeed strong. So it's going to be SN2 or E2. Well, to figure out that, if we look at steric bulk, there's really not much different around the secondary carbon on the thing with the leaving group, our electrophile, and then there's not much steric bulk on the nucleophile. So that's not going to help us out any. Looking at the pKa though of this, right? If we have the sulfide in this case, and then we look at the conjugate acid, it will be the one with the proton attached there. And this conjugate acid is in our pKa table. It has a pKa of 10. All right. Looking at that pKa, this right here tells us that it's not that basic. So this is going to indicate SN2. And as a matter of fact, that's what we're going to be doing. This must be an SN2 reaction. Okay. So knowing that, what we're going to see for the mechanism, as is with all SN2s, the nucleophile, which in this case is our sulfide, so that sulfur with the negative charge, is going to come around. It's going to do a backside attack, displace our chlorine. And the one thing that we really need to keep in mind about our SN2 reaction is it does invert the stereochemistry, right? Because it does a backside attack. So keep that in mind when you're drawing the products, because if you don't do so, it's going to be incorrect. So it inverts our stereochemistry here, which means where we draw our product or the predict the product, it should have the thioether on the dash. All right, let's do another one. So, example 7 here. Let's say our starting material is this here, and we do a reaction where we just add methanol at 60 degrees Celsius. Well, for this, starting out, we see that our leaving group is on a tertiary carbon, right? That tells us that this cannot do SN2 right off the bat. And the other thing is looking at this, there's no charges. So this is a weak nucleophile slash base, which immediately tells us that this is SN1 and E1. Okay? So looking at that, we're going to look at the mechanism behind these. So for this reaction here, the first step is always the same, right? Because we start out with our leaving group leaving, so that bromide just heads out. And now what we have is a tertiary carbocation that is in fact stabilized by resonance, right? So this guy is also not going to do any rearrangements because it is technically the most stable carbocation we can form, all right, of any. So that means that we're going to split into two paths here, right? For the top one, we'll be showing what happens for the SN1. For the bottom one, we'll show what happens with the E1. So for the SN1 pathway, our methanol, which is our weak nucleophile, is going to come in. It's going to add to that carbon with the carbocation, so it's going to form a bond there. And then keep in mind, this is going to be racemic. right? From here, we're going to see that in order to finish up and form that SN1 product, this is going to then grab the proton that was left over on the methanol that we added, and that ends up giving us our final product, which is an ether. Okay? For the E1 pathway, right, because that is our SN1 product. For E1, we have multiple alpha positions to consider, right? Because remember that E1 will always form the most stable, most substituted alkene it can. So in this case, since it's on a tertiary, there's three alpha positions. There's one here, here, and here. Now then, looking at these, we can say if we were to form an alkene here, this would give us a tri-substituted alkene. If we formed one here, it would be di-substituted. If we formed one here, it would be tetra. So we would say that going for the tetra is the best. But if you look at it, this carbon that we're looking at already has four bonds shown. So if this already has four bonds shown, that means there's no hydrogens there to take. Since there's no hydrogens there to take, that tells us that we actually cannot form this tetra-substituted alkene. Instead, we're going to have to settle for second best, which is the tri-substituted alkene. So in order to form that, we have this hydrogen that's on that alpha carbon. The methanol will act as a base, come around, grab that proton, form the alkene, right, which is that tri-substituted alkene that we were just talking about. And remember that for this, it is going to have to be E because E is more stable and thus better for an E1. So that would be our E1 product. Okay, so in the end, whenever we're drawing the predicted products for this reaction, we would draw both the SN1 product and the E1 product. Okay, so we have three more examples, right, that we will just be going through. So three left, and then we will move on to the next topic for the next lecture. So for this example, we have this as our starting material. And we're going to react it with ethanol at 50 degrees Celsius. So for this reaction, what we're going to see is that first things first, we have to identify what's going on. Our leaving group is on a secondary carbon, and then we do not have a charged thing here. So this nucleophile is weak. So we already know that this is going to be SN1 and E1. All right. So looking at what's going to go on in the mechanism though. This one, of course, is going to be very similar to our previous one, but there's going to be a couple things that change. First off, looking at this, it still starts the same as every other mechanism for SN1 or E1, where we have our leaving group leaving. Whoops. Upon it leaving, we form a secondary carbocation, right? We always have to check for rearrangements. And in this case, there is going to be one because we have this secondary carbocation, but adjacent to it is a tertiary hydrogen, right? It's on a tertiary carbon. And so because of that, what we'll see is this can do a rearrangement, right? If it does this hydride shift, what'll happen is we now have the carbocation in this tertiary position. So we have our tertiary carbocation. So with that rearrangement occurring, now the question is this our most stable carbocation? The answer is yes, right? We can't do any better. There are other tertiary carbocations we could form, but those are the exact same, and we'll never do a rearrangement if it's the same thing. So from here, now we will split and do our SN1 and E1, just like we've done all these times before. So the bottom path will be E1, this top one will be the SN1. So for the SN1 path, from here, the ethanol acts as our nucleophile. comes in and adds. And so at this point, you have the protonated oxygen right there. Of course, just like in every other mechanism that we've been seeing for SN1, some more ethanol is going to come on by, help that out. And so that will form our SN1 product that I'll draw up here. And then for our E1 product, thinking about what will form the most stable, most substituted alkene, we can actually form a tetrasubstitute alkene if we pluck from the alpha carbon over here. So we will do so. We'll grab that proton, form the alkene, and that will give us our E1 product, which is that tetrasubstituted alkene right there. So this is a reminder that you always need to check and make sure those rearrangements exist, right? Because the products would look very different if you tried to draw these without noticing the rearrangement. Okay, so let's do our second to last example. So for this one, we're going to do sodium hydroxide and DMF at 90 degrees Celsius. For this reaction, looking at it, we first have to identify our leaving groups on a secondary carbon. And we, of course, have a strong nucleophile because it's just the sodium with the hydroxide anion. And this, of course, is strong. So we can do either SN2 or E2. And looking at this, it originally looks quite a bit like an SN2 because thinking about hydroxide, right, its conjugate acid is water. And water is, of course, the defining piece of a pKa scale at 14. So theoretically, this shouts SN2. But the one thing that you have to be mindful of is that it's not always just about the exact sterics of what you're looking at, right? Because this is small, and then we're sitting on a secondary carbon, which tells us that we can generally do an SN2. But the thing is, even though this carbon right here is secondary, look at the carbon right beside it. It is quaternary, right? Quaternary carbons are super bulky, aka a lot of steric strain. And this is why, if you look back in the notes, right, if we scroll all the way back up to right here, we stated in this little grouping sterically hindered base or carbon surrounding the leaving group. The reason for that is examples such as this, where we now have this quaternary carbon that is close to our leaving group. It is adjacent. And so what this is going to do is SN2 will be very slow. What's not very slow, though, is E2, right? And so because of that, what we'll see is that this is instead of doing an SN2, it's going to follow an E2 mechanism. So we always want to make sure that we're paying attention to not only the carbon and the sterics there, but the sterics surrounding it. Because in this case, for the mechanism, what we're going to see is if it's E2, we're going to form our alkene. Zaitsever-Hoffman doesn't actually make a difference in this case because the only alpha protons are the ones to the left, right? Because this right side is all carbons, none of those are useful for us. Instead, on this left side over here, there's definitely going to be a hydrogen on the dash, and so our hydroxide will act as a base, and it'll do the E2, where it grabs that proton, forms the alkene, kicks out the chloride, and we end up with the alkene as our product. Okay? So, just as a reminder, when you're looking at SN2 versus E2, you need to pay attention to a lot of factors. Okay, before we do our final example, we're going to have to talk about something called reaction equivalence. Now, you all have actually been using these in lab quite often, right? But essentially, what these are doing is they tell us how many times a reagent is there compared to the limiting reagent. And the reason this matters is because some structures can do multiple reactions from a single type of reagent, right? And so what this means is when we're looking at this, one equivalent means that the thing is going to do a single reaction. But if we add something like two equivalents, right, two reaction equivalents, that means that it is two times the limiting reagent and thus can do two reactions. Okay? The same thing is true of there's another thing that you may see written down that is excess. And what excess is essentially saying is it is infinite times more than the limiting reagent. AKA, it can react a lot. So in this last example, we're going to look at something that uses multiple equivalents. All right, so let's take this idea and say, okay, well, what happens if we took sodium hydroxide, two equivalents of it, which you'll see either written out fully as equivalents or just EQ, and DMF at 80 degrees Celsius? Well, what'll happen is it'll be able to react two times, right? That's exactly what this is saying here. It can react up to two times, right? Keep in mind it doesn't have to if a reaction can't occur. So in this case, looking at this, sodium hydroxide we already know is strong, right? Because it has that OH minus, so it is strong. And then the types of carbons our leaving groups are on, we have two chlorides. One is on a primary, one is on a tertiary. All right. What this tells us is a primary with a hydroxyl is going, or hydroxide is going to do SN2, right? So this first equivalent can do SN2. And so what that's going to look like is essentially the hydroxide, which we'll label as equivalent 1, will just do a backside attack, kicking out that chloride. And the reason for this is that SN2 is very, very fast on primaries. Right, from here, we've used up one equivalent. We have one left. What's that going to do? It's actually going to do an E2 reaction. And so our second equivalent can then do another reaction where it grabs that proton, forms the alkene, kicks out the chloride, and we've ended up forming this structure here as our overall product. Okay? So the moral of the story is more equivalents is more possible reactions. All right. So if you see multiple equivalents, just keep that in mind that it could be doing more than one thing. So this is a general framework that I would suggest using as you go through and you practice these problems. Identify the problem, right? Find out what reaction's going on, and then use that information to take that reaction type, put it into an actual mechanism to figure out what product you're forming, and then that is the answer to the question. Okay. With all that being said, next time we will look at one last piece of weird things with SN1 and SN2, but this is primarily the main points that you need to get across for the big four reactions. And these are the types of questions you'll see on your exam. So I'll see you next time as we talk about what are called intramolecular interactions.